Everyone. In simpler terms, this is a study I was invited to participate in where we looked at the needs of the crew in terms of consumables and compared that against losses and what would be needed for resupply. Looking for the tipping point on where that resupply requirement starts to exceed the mass of the equipment that it takes to produce it. That, for engineering, is the tipping point for where they would start to consider in situ resource utilization. I look at it a little bit differently as a geologist, but the engineers are a little more practical. I want to just thank my co-authors, Greg Gentry and Matt Duggan of Boeing, and a number of folks at Hamilton Sundstrand. So what we wanted to look at was estimating the life support oxygen, nitrogen, water losses for the crew lander on a Mars or lunar surface habitat. It's important to point out that this study does not include propulsion, which I think we'll find that tipping point to come a lot earlier. So we're specifically looking at consumables for the crew. We want to look at early viable candidates for life support and conducts the trade studies that were needed to identify that crossover point. And then inform architects and planners with the results. So there's a lot of data in these charts. I'm not going to drill into each and every value, but I will talk about the important summary points that lead up to the conclusions. So we have to start with some assumptions. So for our basis of analysis, we looked at 4 crew. The lunar stays over a range from 30 to 180 days, and for Mars, looking at a short stay and a long stay. The HAB was 85 cubic meters, including all the life support functions expected of a HAB. We have 1 pedestrian airlock and 1 rover docking port. We have a shower and a laundry, and this turns out not to be a big driver for renewables. We were quite conservative, I think, in terms of our EVAs. They use the term pedestrian surface excursions, I think, to draw a difference from walking tours to excursions with the rover. And it turns out that whenever the crew goes outside, that's where the largest losses in consumables occur. The reclamation, the ability to reclaim that stuff from the suits or from the rover is not part of the thinking. We looked at as delivered food water content, and that was a variable. So you deliver the food either bone dry or 50%, adding 50% water, and that actually turns out to be a larger driver than I would have thought. And then for the moon, we looked at landing at the poles using lunar polar resources, not really regolith mining to extract oxygen from the regolith, rather extracting resources from the ice at the poles. And on Mars, initially just looking at extracting what we needed from the atmosphere, and that's primarily for the inert gas renewables. There certainly is a potential for water on Mars, or for processing water on Mars. However, initially I think we'll be landing at the mid to lower latitudes where we really haven't, at least to my knowledge, haven't found water in quantities that we can process. It's not to say that it's not there. It may turn out to be a deep drill or perhaps some buried ice in a rocky glacier. This is a slide I'm not going to try to explain other than to point out that we're basing this on what we know from our experience on the ISS and the way those systems have to go forward. As with any discipline in the business we're in, we have our own language, so they have their own, and I've included a an acronym list at the end, because I don't know what a lot of these mean without looking at that list. But you can see that we need to make some improvements on some of these systems, but not all of them. This is a schematic of the systems for the HAB and the rover for you to look at your leisure. I'm not going to try and plow through all of those. So the baseline consumables and waste, these are your gazintas and gazoutas, and you see that they balance. Basically the baseline is 10.35 kilograms per person per day, and the total need for the crew. Something one of these fellows pointed out to me that got me thinking about whether I would really want to do this is think about boarding your spacecraft with your bag of water that you have for the course of your 2-year mission, and that plus what your other crew are bringing along in a closed system, that's what you got. I think I would like the way to flush that system out and maybe have some fresh supplies, but that's where we are. So this is the look at the losses over time, and you can see that cooling the suit is really the big driver for water losses. The data looks at 50% water in the food versus 0% water in the food. For the losses, it's not a big driver. For the water needs, it is a bit larger. So here's the summary of the water needs and the water supplies. You'll see that there are these are negative deltas per day, depending on the water in the food or the number of EVA. So the regenerative systems, and these were systems I think running at about 99% efficiency. So you're going to experience losses that you're either going to have to haul the stuff with you or make up from ISRU. Yeah. I think these slides are going to be available online. Yeah, so, or talk to me later, I can get you a copy of it. Here's a table of the resupply needs, and you see they go up quickly as your excursions. Now I've been on a mission simulation, and I know the crews, these estimates for EVAs are probably very conservative. They're going to want to get out more than that, but the more you get out, the more you're going to lose in terms of what you brought with you. So the initial supply estimates, this number for 1 month, that's a number to consider, and I'll have some other things to say about that later, but that's the need for potable water for, say, a 1-month contingency. And if you want to go to 3 months, it gets even higher. So adding your needs for contingency really starts to reinforce the need for ISRU. We know there are multiple lines of evidence for lunar polar water, lunar hydrogen. The regolith has abundant oxygen. However, we didn't consider it for this study, and this study really is looking at early mission planning. For later missions or for other locations, certainly you want to look at processing regolith. So for the study, we used the results of the L-Cross experiment, not having anything else, and that L-Cross number may end up being conservative, so there may be a possibility of even having greater, but we use 5.6% by weight mass of water in the regolith at the poles. And chart showing the available gases at Mars. However, without the availability of water, you'd have to take your hydrogen with you. So finding water, I think, is going to be key in those first couple of missions. This shows our basis of estimates for the mass of the processing system. I want to point out that this is really a simplified look at what's needed. The actual masses may differ, but we needed to have a point of departure, so we used terrestrial analogs for finding out what that mass was. And then same for the processing equipment at Mars. Also shows how much gas you need to process to replace your losses. So about 4 cycles per month. And this is the results of where the crossover occurs. So for each of those categories for water and inert gases, where the crossover point, considering the mass of the consumables against that 820 kilograms of production material that you need. However, if you start adding in the tank mass that you're going to need for storage, that number comes down quite a bit. And over on the far right, if you add the storage that you need even for just a month of contingency, your ISRU becomes immediately applicable over a range of stays. On Mars, if you can bring down the mass of your processing equipment, it also brings it down. Like we assume 600 kilograms at Mars, but if you could bring that to 400, the crossover point becomes immediate. And certainly, if you start processing water on Mars, your needs would amplify. This is just a chart graphically showing where those crossover points are for water, and how if you stockpile it, the needs are immediate. Not so much for the inert gases, but that's going to depend on mission duration and mission duration. I'll just leave it at that. So to conclude, you get water and inert gas resupply beneficial within the first mission. Can be beneficial during the first mission, depending on your assumptions. Water mining for Moon and Mars would provide direct benefit. And inert gas utilization is difficult on the Moon. Although I think it warrants further study, there is some nitrogen available for replacement. I'm not real familiar with where you would find it and how you process it. And then the comparisons for what we use for making the assumptions for the equipment. Bottom line is we think this needs to be developed as part of any lunar or Mars habitat, and that should start now. Any questions? Thank you. And your Rosetta Stone.
Is there going to be a quiz?
No, don't quiz me on the acronyms, Jim.
I was going to ask you about that. So Kurt, so really excellent. So there are indeed, as you alluded to, lots of mid-latitude and actually lower latitude ice deposits on Mars that are below a protective sublimation residue, but they're plentiful. I mean, we've seen them with Sherrod, et cetera, and they're just all over the place. So we can guide you to those. I'll send you a couple of papers.
That'd be excellent.
And there's a little digging involved, but
yeah.
Nonetheless, if you break the bag, so to speak, it would be right there, and I'd be digging like hell if I.
Yeah, I'd be digging like hell, and this stuff really changes when you start looking at propellant, the mass of the propellant, and I've got these guys to start thinking about producing water from the Moon to take to other places instead of hauling that stuff up from the Earth. Yeah.
Okay.
Yes, the mining. If you're mining, if you're processing the methane LOX, which is probably the most practical fuel to come back from Mars with, You also can relatively easily produce quite a bit of oxygen. And yeah, the case for Mars assumes that until you know a solid source for water, you bring hydrogen, you're probably going to lose about 10% of it in the 8 months or so before you start really using it off. But the rest is all atmosphere. Nitrogen is almost 3%, but once you remove most of the carbon dioxide, the nitrogen and argon are most of what's left.
Yeah, actually during one of these processes, we're producing excess methane and oxygen, which we end up venting. And I think we probably don't want to do that if we start expanding our thinking. I have time for Jake?
Yeah.
Jake Bleacher, Goddard Space Flight Center. In working with the ISRU community a good bit, as Jim was talking about, the science community is starting to identify a lot of these sites where you could potentially go to. Then there's the next step of the prospecting part to actually map out and know exactly how much is there. And then there's another step in there that often gets overlooked, which is kind of the environmental monitoring. Once you bring that big front end loader in and start to dig it up, you know, how much of it do you actually get into the bucket you're going to?
Right.
So if you have, the analogy I like is if you have 2 trees, you can map out 2 trees, and if you assume you're going to get 2 trees when you cut them down, that's fine. But if you cut the first one down and it kills the second one in the process, you have to anticipate that. So I think what you're showing here is good for us to help demonstrate how we need all these steps, and a lot of them cross over into science, which is of high value to us as well. So anyway, I just wanted to say that.
I agree. There's a lot of maybe oversimplification in this. There's another area we didn't really discuss that's going to have to be looked at, and that's planetary protection, because there's venting from the rover and venting from the HAB that maybe we could filter, but you're still going to be venting gases.